When we looked at various patterns over lists, map, filter and so on, what we did was realise those as functions that take other functions as arguments. What I want to do here is talk about the converse to that. That is, functions that return functions as results. And we're going to look at two particular examples in this short activity, and then there's another activity for you to do some homework to explore those further, and there's a couple of more challenging exercises at the end which you might like to do or not, as you wish. So before I do that, it's slightly confusing in Erlang. There are a number of different ways that you can write down a function when you want to pass it in as an argument, for example. So here we see an example of how to define the all areas function by applying map. And supposing area is defined in the same module, what we do is call list map, and then we say we want to apply this to a function, so we say fun, and then we give the name of the function and its arity. So we've done it by saying fun area /1. If we're in a different module, or indeed in the same module, we can do this, we need to refer to the function by both its module name and its function name. So here we say we want to map the fun in shape : area, that is the function area in the module shape, and again we say its arity is 1. If we're in the shell, then it's possible for variables to be bound to functions, and then it's quite simple, we just write area. So when functions are bound to variables, then it's easy to describe them. But the point being, we can't just use the atom area here, because that we just think of as an atom. So if we want it to be interpreted as a function, we have to say it's a function here. So that's a perhaps slightly unattractive, inelegant part of Erlang's syntax, but it's just worth being aware of that. And of course there is one other option where we could just define our function directly as a fun expression, and I'll give you some more opportunity to define fun expressions in the next activity, where you've got some exercises to try out. So this is how we write down functions, just to remind you of that, the way that we do that. Now, one of the nice examples that we get in a functional programming context is when we do what's called partial application. Now, we think of plus, it's an operator, you give it 2 numbers, it will give you back a number. What happens if we apply a function, if we apply an operator to one argument? So here we've got add of x. What could the result be? Well, the answer is, of course, it's going to be a function that adds x to its argument. So it's the function that takes y and returns x plus y. So add x, it's add 3. What would add 3 do? Well, you give it a number, 7, it gives you back 10. You give it a number, 33, it gives you back 36. So add 3 is an operation that takes one argument. And then we can use that in defining other functions. So we've got a function add that has a function as a result, and we can use that result where we expect a function. So here's an example. If we want to add 1 to everything in a list, we can do lists map applied to the function add 1. That's add applied to 1. Remember, that's the function that adds 1. It's fun y goes to 1 plus y and x's. And then indeed that could be applied to a variable. So add to all takes a number and a list of numbers and adds that number to each of the elements. And what we do is we map the add n function along the list, because add takes a number and returns a function. So add n is a function. It's a function that takes y and returns n plus y. So here you see we're able, once we've got functions as results from one function, we can pass them into a function that expects an argument that's a function. So now we're really dealing with functions as data. And this is where we begin to see the power of this functional programming approach. So there we've got these partially applied functions. Okay, so that gives us, that's one sort of function as a result. Now let's have a look at an example. Oh, sorry, and just to, before we move on, I wanted to say something about what these functions get called. This sort of representation of a function, of addition as a function that takes one argument and gives you back a function, which you could then apply to another argument, this is called a curried representation. Nothing to do with the food, it's all to do with Haskell Curry, who is a pioneer of the lambda calculus, which was one of the things that, one of the theories that fed into functional programming, developed first in the 1930s. And of course after, Haskell is named after Haskell Curry as well. So this curried representation is partially these functions where you take one argument at a time, like my representation of add on the previous page, on the previous slide, is called curried. Now, let's look at a final example of a function that takes functions as arguments and returns functions as results. And you've seen, we saw it in the previous activity, we often do function composition. I applied lists map and then applied lists sum to the result, for example. First we want to do one function, then we want to do another. We can define a function called compose that takes f and g as arguments and it returns a function. And what is that function? It's a function that takes x and returns g of f of x. So first f is applied to x and then g is applied to the result of that. So compose now is a function that has two functions as argument and returns a function as result. So here we're working, instead of having a function with two numbers as argument and a number as result, each of the arguments and the result are themselves functions. And that's the sort of thing that we start using when we're doing functional programming. You'll see more examples of this in the rock, paper, scissors case study, and also when we start doing simplification in the language processing masterclass that forms the final example of this functional programming MOOC. So the result, as I've said, is a function. And just to summarise, we've seen functions which take functions as arguments, like map and filter and so on. We've seen functions as results, the curried functions, like the add. And we have some functions where they have functions as arguments and results. Let's compose and iterate that you'll see in the exercises. So now you've seen, I've reminded you about what's going, how you write down functions and also how we define functions that are higher order. We can get back to our case study of rock, paper, scissors after you've tried some of these things for yourself. Okay, good.